Hello, this week we're going to be looking at performance measures, or how to calculate or measure if our classification is good or not, or compare to different classifications. Okay, so we're going to be looking at several measurements. We're going to start with accuracy and percentage error. We're going to look at in more detail at the results using a confusion matrix. We're going to look at precision and recall values and combination of both of those measurements into the F1 score, and we'll look at the area under the curve. So we're going to have a look at the concepts, what we mean, how do we calculate it by hand, and then how we calculate it using scikit-learn. Okay, let's start. Okay, so the classification accuracy is going to be the number of correct predictions divided by the total number of predictions, multiplied by 100, so we get a percentage. For example, let's have a look here. Okay, so we have our notebook, and we're gonna go into our module scikit-learn metrics, and we're gonna import the accuracy scores. We're gonna have these values of predicted categories. So the first one we predict 0, the second one 2, the third one 1, the fourth one 3, and the real values for those are 0, 1, 2, 3. Okay, so if we look at it, we can see that the first value is correct, the second one is incorrect, the third one is incorrect, and the fourth one is correct. So there's 2 correct out of 4, so it's a 50%. And when we try that with our accuracy score, giving it the true values and the predicted, it gives us the 50%. Okay. Now I'm gonna ask you to open up on web courses the Excel file data exercise 1. There's 2 sheets. One contains the predicted values and the other one contains the real true values, and I want you to import those into your notebook and calculate the accuracy for those values. Okay, and we have here the example and your values for your accuracy. Okay, so what we get here is a percentage. The one we used in this example, we're getting 50%. That means there is also a 50% percentage error. Okay, so the error is whatever is left until you get to 100%. So if you had a 95% accuracy score, you would have a 5% error. Okay. Now sometimes, depending on the nature of the values that we are getting and how many categories we have and how balanced those categories, if we have the same number of zeros as we have the same number of ones, then the values of the accuracy might not represent the accuracy really of the performance of the classification method. Okay, so sometimes we might need to, it could be the case that we have 2 categories. One has 95% of the values, the second category has 5% of the values, and most of the values in category 1 are classified correctly, but all of the values of the second category are classified incorrectly. And in that case, even though the accuracy score would be quite high, it's not really a very good system if we're missing every single value of one of the categories. To have a better look at what's happening with our data and our predictions, we can use what is called a confusion matrix. Basically, it's a table where we can see each of the predictions, if they are classified correctly, and if they are not, where were they classified. Okay, so it's be easier if we just get our table. Okay, so here we're gonna have 0, 1, 2, 3, then 0, 1, 2, 3. It's going to be a little bit empty because we only have 4 predictions. But if we remember, let's go back to our data. Okay, so these were our values. So our predicted 0 was from category 0. So we go to the first box on the table, put a 1. here. Okay, so when we predicted a 0, it was a real 0. Let's go back to the data. In this second case, we predicted a 2 and it was a 1. So on the table, we're going to come predicted 2, but it was really a 1. So that's over here. Now we go back, we predicted a 1, but it was really a 2. So if we go back to our table, so we predicted a 1, but it was really a 2. Goes here, and then the last one we predicted a 3 and it was a 3. Okay, so as you can see, the values in the diagonal are the correct predictions. The values around outside the diagonal are incorrect predictions, and they give us an idea of how incorrectly and maybe why are we getting those values incorrectly. Okay. So instead of just having the accuracy, we can add our confusion matrix and we get a lot more information of what's happening with our predictions, with our classifier. If we use scikit-learn, there is a command, a method in this package called confusion matrix, and we just need to give it the true values, the predictive values, and it will create our matrix. Let's have a look at our, oops. Okay, so we import the confusion matrix, true values, predictive values, and we get our confusion table. Oops. And if we run it, let me go down a bit. When we run it, we get our matrix created. There. Okay, so those are the values. For this particular, these are different values than compared to the ones that we used in our small calculation. But you can see here we predicted a 0, it was a 2. We predicted, we only have 3 values here, so there's 3 columns and 3 rows. And we predicted a 0 and it was a 0, and the same here, 0 and it was a 0. So those go, this 2 represents this value here and this value here, and so on. Okay, so you can see how there's a lot more information. So the confusion matrix gives us more information. We can't really compare two classifiers using the confusion matrix. It's more to know what's happening in the background. And as we were saying earlier, if we have data that has two classes, let's say, and they're really imbalanced, okay, then the value of the accuracy is not going to be useful. The confusion matrix will help us identify that we're actually misclassifying every single value of one of the categories, and we might need to use, if we want a number to compare one classifier with another classifier to see which one is performing better, we will need different measurements. And in this case we have three really measurements. It's 2 precision, recall, and F1 value, which is F1 score, which combines precision and recall. So let's have a look at what these mean. Okay, so precision is the number of true positives divided by the number of true positives and false positives. So basically it means how many real good values, or how many of the predicted values for one class, like how many of the values we thought were going to be 0 were actually 0 in the truth value. So it's a measurement of how exact, how many did we misplaced. Okay, now if we look, we compare that with the recall value. Recall is the number of true positives divided by the number of true positives and the number of false negatives. So it's really how many of the real values that should have been predicted did we get for this particular one class. Okay, so for the recall, for the precision, we were saying of all the ones that we said were going to be of class, say 1, how many of those were accurately classified? So how many were supposed to be 1? And then on recall is out of all the values that should have been 1s, how many did we actually capture? So it's seen as a measurement of completeness. Out of all the ones we should have gotten, how many do we have? Okay, And then we have the F1 score is just basically combining those two into one number. Okay, there's different F scores. The F1 score means you're given the same weight for both precision and recall. There's other F scores that would increase the weighting on one or the other. Okay, in our case we're just going to use F1 scores. Okay, and in order to calculate these values for a particular set of data, we have our methods: precision score, recall score, and F1 score. And I'm going to ask you to try those with the data from data results 1 and see what values you're getting. Before we get to that, I can show you the example. So for the y true and y predicted that we had here with the 0, 1 and 2 classes, we are importing precision score, recall score, and F1 score, and we are just using the method true value, predicted value, and then we have to decide which way we want to calculate the average, because we are calculating the precision, recall, and F1 score for each of the classes. In our case, if we go back to our data once more, in our case for these particular values here we have 3 classes, 0, 1 and 2. Okay, up here. And that means that the precision value is going to be calculated 3 times, the recall value 3 times, and the F1 value 3 times. And there's different ways of averaging those. In this case we're just going to use micro average. Okay, and we're getting this 0.66, 0.66, 0.66. Okay, so now we just have one more measurement to combine or to compare different classifiers, which is the area under the curve. Okay, so in this case what we're calculating is the area under the curve, thinking about plotting our xy values, having a line that is y equals x, that is the 0.5 here. Okay, and that will be kind of like 50-50, so random guessing. Okay, so any value higher than that means that your classifier is doing a good job, and the highest value you can get is 1. Okay, okay, we can look at an example here. Okay, and make this good. Okay, so you have we have the true positive rate here, the false positive rate down here, and the area under the curve, or sometimes you'll see it as receiver operating characteristic or curve. So this line here is the 50-50, and every time you get a true positive you go up, and every time you get a false positive you go across. The higher you're getting, the more area that this curve has underneath, the better your classifier is. Okay, we're not going to get into the details of the curve, but just so we know that it's another way of comparing different classifiers, and it's useful when you have to evaluate performance on unbalanced data sets. Okay, so remember we were saying earlier that there is an issue with unbalanced data sets and the accuracy measurement. We said that we can check with the confusion matrix what happens, the details of this classification. We can also look at precision and recall values and the F1 score. But if your data is very unbalanced, then the area under the curve is a safer way to compare. Okay, how do we calculate this value for the area under the curve? In order to get value, let's say these are our y values, these are our predicted values, we need to calculate the curve, and that will return the false positive rate and the true positive rates and the threshold, our line, and then we send those two arrays into the area under the curve, and this will give us a score. Okay, we try in using scikit-learn. We have here, we import matrix, we send our true values and predicted values to the receiver operating characteristic curve, it returns our false positive rate and true positive rate, and we send those to the area under the curve value, and that gives us one value, which is telling us that in this case it's not very good. Okay, but you can see how you're getting different values from what we started earlier on. We were saying there was a 50% accuracy, then we have a 0.6 precision, 0.6 recall, and our 0.6 of area under the curve. Okay, so we had to compare these results from one classifier with the results from a different classifier. Depending on the nature of the data, the area under the curve might be better if your data is unbalanced, or you might have enough with your accuracy and or precision and recall values. Okay, so that's all for this week. You have an exercise to work with the data that is you can find on web courses and go over these precision performance measurements and calculate the values. Okay, and we'll continue next week starting with our classifiers. Okay, that's all.